Have a look at this building's floor framing. Let's focus on the core walls at the upper part of the plan. Let's label these core walls as core wall A and core wall B. Focusing further, we have plotted roughly the tributary floor areas that are being carried by each core walls. The gross weight carried by these core walls shall be transferred to the ground foundation. The gross weight shall be the weight of core wall's full height, plus all the combined floor's weight in each tributaries. The gross weight carried by each core walls at the base are calculated from the estimated data as shown. Note that we are calculating here self-weight or dead loads only. The estimated gross weight carried by core wall A is equal to 3,640 tons, whereas for core wall B, it is equal to 3,690 tons. Now we can calculate the axial compressive stresses for each core wall at the base. For core wall A, the gross weight carried is equal to 3,640 ton divided by core wall area equal to 5 square meter. Hence, axial pressure shall be 7.1 for megapascals. Note that this is for static condition only. When earthquake occurred, we increased the weight with dynamic amplification factor of at least 30%. Now, the axial pressure is equal to 9.28 megapascals. For core wall B, the gross weight carried is equal to 3,690 ton divided by core wall area equal to 5.2 square meter. Hence, axial pressure shall be 6.96 megapascals. Note again that this is for static condition only. When earthquake occurred, we increased the weight with dynamic amplification factor of at least 30%. Now, the axial pressure is equal to 9.05 megapascals. Have a look at the table shown. It defines the permissible stresses in compression of concrete. This is dictated by the grade or strength of concrete used in the construction. We will come back to this later. Let's review the column failure mechanisms. Long, slender columns breaks from buckling, while short columns breaks from compression and/or shear. Going back to core walls. Shown is core wall A, as well as core wall B. The climbing tower crane is positioned on top of core wall B. Let's evaluate the strength or the load carrying capacity of both core walls. Let's assume the concrete grade or strength is 5,000 psi, or the M35 type concrete. The allowable direct compression strength shall be 9.0 megapascals. For the static case condition, the direct compression stress for core wall A is equal to 7.1 for megapascals, whereas for core wall B, it is 6.96 megapascals. For both core walls. For the assumed 5,000 psi concrete grade, both failed the compressive strength limits. During the earthquake state, note the pressure stresses are calculated from self-weight or dead load only. If we include the live loads and wind loads to the statics case, it will also fail. For M50 type concrete grade, or 7,500 psi, the permissible limit is sufficient for the calculated axial stress. But again, we reiterate that live loads and other loads are not yet considered. 7,500 psi may also be insufficient. We need at least 10,000 psi concrete grade. We must note that the concrete must also be of good quality in accordance to approved design and specifications. The estimated compression stresses for both core walls are nearly the same. This is where the effect of climbing tower crane came into play. The crane weight is offsetted from center mass of the building. This is generating an eccentric loading to the building. We can also consider that the core walls are tall, slender tubular columns and braced laterally on each floor levels. The tower crane being applied on top of the core wall will impact more on core wall B. Also, the oscillation or swaying motion of the tower crane also induced bending moment on the support floors directly carrying the crane. The magnified earthquake-induced compressive stresses on the core wall B is further magnified by the oscillation, swaying, and vibration induced by tower crane. The videos have clearly shown sudden collapse on the core wall side. When core wall B snapped, core wall A also snapped. The building leaned to that core wall side as it continuously falls down. The front side and side columns collapses thereafter. Watch again the videos, played in very slow motion. Let them find out the concrete and steel grade used in the construction. For now, we will consider the study review as concluded.